Good afternoon, all. Welcome to the fourth section of Summer School on Algorithms. In this section, we are continuing Approximation Algorithm by Professor Muralidhara. I welcome Professor for giving the talk. Over to you, sir.
Okay, so today again I'll be talking about two more approximation algorithms. In the last session, we have seen approximation algorithms for the vertex cover and the TSP. So what we have seen is how do you get approximation algorithms even when you don't know the optimum. What we used was what is known as a lower bound, right? So through the lower bound, we were able to make the connections and show that even if you don't know the optimum, we still guarantee approximation algorithms. For the vertex cover, the matching was the lower bound, and for the TSP problem, MST was the lower bound. And so today we are going to see different techniques. The other techniques are, so one is the algorithmic technique. We're going to see two problems and design approximation algorithm for that. So I have chosen two easy problems, relatively easy problems. Everybody should be able to understand the approximation algorithm for these two problems. The emphasis here again on techniques. One of the problem uses dynamic programming as the technique to get approximation algorithm. And the other problem, we get what is known as local search. Okay, local search algorithm, which will give the approximation algorithm. And we will also show how rounding helps. Rounding is a technique which is widely used in design of approximation algorithm. And one of the problem also admits what is known as FP dash. Okay, so that is fully polynomial time approximation scheme. So you will learn about all these things. For a change, in the last session, I only chose a minimization problem. Today, we are going to talk about both the problems that I have chosen today is maximization problem. So when I talk about maximization problem, we want the answer to be E of x, an alpha approximation algorithm was defined for the minimization problem as A, the way the answer written by the approximation algorithm should be smaller than alpha times the optimum. So where alpha is essentially greater than 1. So in the case of maximization problem, what we are saying is that the answer given by the algorithm should be greater than or equal to alpha times the optimum, where alpha is smaller than 1. Okay, so the answer is 100 and I want to maximize. I should guarantee that the answer that I get is at least 90, right? So that's the kind of results that we are looking at. So with that note, let's just look at the first problem. The first problem that I have chosen is the classical problem called Knapsack Problem. So in this problem, we're given n items. The weights are given and the profits are given. And the knapsack of integer capacity W is also given. We will also assume that the WIs and PIs are also integer weights. Okay. The knapsack of size W is given. We want to pick some of these items such that the weight of the items that I pick will fit into the knapsack. That means some of the weights of the items that I picked is smaller than or equal to W. Among all such options, I want to pick the item so that the total profit that I make is maximum, right? So you can easily write an integer program for it to just to understand. We can associate a binary variable to each of these items. X of I is 0 if I don't pick the ith item. X of I to be 1, then I pick the ith item. So what we want to do is that we want to find a solution such that sum of x of I into w of I is smaller than or equal to w, but we want to maximize sum of x of I into p of I. I repeat, maximize sum of x of I into p of I such that sum of wi into x of I is smaller than or equal to w. So this is a classical NP-hard problem. There is a fractional knapsack problem. where you're allowed to pick a fraction of an item. Simple greedy algorithm will give a optimum solution for that. Okay, but this is an integer knapsack problem. So here the integer essentially means that you are either allowed to pick an item or you don't pick an item. So you can't take a fraction of an item and get fractional profits. That's not allowed. We'll also make some more assumptions. Let's say that capital P is a maximum profit that you can make, right? So essentially means you look at all the PFIs, the max of that we are going to call it as P. We'll also assume that each of the WI is smaller than or equal to the capital W. That means that every item that is under consideration can fit into the knapsack. If there is an item which doesn't fit into the knapsack, then obviously we're not going to pick that in our solution, right? So we can as well assume that such an item doesn't exist. Okay. So the assumptions are each of the WI is smaller than the size of the knapsack. That means that if you look at each item, so it can fit into the knapsack. And the profit, the maximum profit that I can make is, that is the maximum of PFIs is denoted as capital P. So since all the items can fit into this, if you pick this P, that one item, that is obviously a feasible solution. So your optimum should be always greater than P. Okay, so the capital P is the maximum among all the profits, and the optimum is the optimum solution to the knapsack problem. So optimum is always greater than or equal to P. So in some sense, this is a kind of a bound for the optimum. So with that note, let me show you a dynamic programming formulation.
Excuse me, sir. There is
Yeah.
a question on chat.
Okay, I'll see. Yeah. Can we take any number of items of the type or it's only 0, 1, right? In this version of the problem, we will only call 0, 1 problem. So if there is an item that you can pick more than once, as an input, you will show it as 2 times. Okay. So if there is, let's say, yeah. So if there are items of weight 10 and the price is, let's say, 5, then if you know that there are 5 such items, so what you do is that is 5 comma 10 can be given input 5 times. Okay. So now after you give this input, now it's either 0 or 1, right? So in practice, what may happen is that there are, let's say, 10 items of same kind. You may take from 0 to 10 of them, right? So that becomes a different variation of the problem. If that is a real problem, so you write the same input 10 times so that it becomes just 0, 1 problem. Okay. So with those laws of generality, we are going to assume that it's a 0, 1. Either you pick the ith item or you don't pick the ith item. That's the formulation that we are looking at. Okay. So let's continue with the dynamic programming formulation. I'm going to build a table. I'm going to call it as W of I comma j. So I'm going to consider only the first I items and I want to make a profit of j. So I'm going to fill this table based on induction on I and j, where the first. So I want to consider only the first I items and I give you a profit of j. So I want to know what is the minimum size knapsack that is required if I had to make a profit of at least j using only the first I items. Okay, I repeat. So this table will store if I am allowed to use only the first I items and I want to make a profit of j, what is the minimum size knapsack that is required so that I will make at least profit of j. Okay. So how do you fill this table? What is the initial step? Suppose if I'm given only one item, okay, and if the profit that I want to make is smaller than P1, then the minimum size knapsack that is required is W1. Okay, but if you want to make the minimum size knapsack that is required is W1. If you give me any knapsack of size smaller than W1, then I can't make a profit of P1. Okay, so notice that here I have at least j. So anything bigger than j is allowed. So but anything smaller than j is not allowed, right? So here this is at least j. Okay, if j is smaller than p of I, so if I make p of I, that's okay, right? Anything more than p of I is fine. So if you give me an knapsack of size W1, I'll be able to make a profit of p of 1, which is at least going to be yeah, it is going to be J. But if you want to make a profit which is bigger than the first items, okay, in that case, I can't. So if you give me a knapsack of size W1 and your intention is to make a profit of J, where J is smaller than P1, I will decide to pick that item. So since I have an knapsack of W1, I can make a profit of P1. So if you wanted to make smaller than P1, then it's always possible. But if your intention is to give me make a profit which is greater than P1, and if I'm allowed to pick only one item, the first item, let's say you can make a profit of 10 rupees. But if you want to make 11 rupees, and if I'm allowed to give only one, it doesn't matter what is the size of the knapsack that I have, I will not be allowed to pick the item, right? I'll not be able to make that item, so I'll just write it as max, right? So even if you give me a knapsack of infinity, I will not be able to make any profit. So this is going, in that case, I'll just set it as infinity. So now once I know how to solve the problem for one, I will inductively try to solve the problem for any general I. Okay. So when you're given the ith item, there are two things that I can do. One is that I pick the ith item or I don't pick the ith item. Okay. And there are two options. I'll explore these two options and pick the one which is best for me. So what is the best? When I take two options, what is that I'm keeping track of? I'm keeping track of the minimum size of the knapsack that is required. So I will take the min of these two options that are available. Because the problem is written as the minimum size knapsack that is required, I will take the min of these two options. What is the first option? In this case, I don't consider the ith item. I want to make a profit of J using only the first I items. Okay, I decide not to pick the ith item. In that case, all the profits that I have to make should be from the I-1 items, right? Since I have decided to ignore the ith item, all the profit should be made from the I-1 item. Okay, let's say that other option that I have is to pick the ith item. If I pick the ith item, I need a size of the knapsack which is Wi, right? I pick the ith item, so that will occupy an extent of I-1, so the Wi, and the remaining knapsack, whatever is the minimum, that should be, you should be able to pick it from the I-1 items, and the profit that I make, because I decided to pick the ith item, I straight away make a profit of P of I. So if the objective was to make a profit of J, then with the remaining I-1 items, I should be able to make the profit of J minus P of I. So this will be the minimum size of the knapsack that is required to make a profit of J minus P of I using the first I-1 items. Let's say that that will occupy a knapsack of this much. But after that, this is W minus P of I. So I need a placeholder for the W of I, which will occupy this much. Okay. So if I pick the ith item, this is what is going to be the equation. I would have already occupied Wi, and remaining from the remaining I-1, I should be able to make a profit of J minus P of I. Okay. And if I don't pick the ith item, then all the profit should be made from the I-1. So the entire knapsack is free for your use. Okay. So we will fill this table. Is this equation clear to everyone? Is there any questions about this equation? There are questions I think you should ask, otherwise we'll move forward. So I think the most important thing in the dynamic programming formulation is this equation. How do you get this? What do you store in each of these state? And once you define that, then how do you recursively build the table, right? So that's what is important. So the definition of W of I comma J and um, right. So the how I'm filling the table. If that is clear, then most of the things will be clear. So this is an extension of recursive approach. This is a standard technique which were used in designing algorithms using dynamic programming. So this technique may or may not work for all the recursive approach. Okay. So what I am going to do here is not recursion. I'm not going to write a recursion here. This looks like a recursion. The way it is written here looks like a recursion, but when we implement, we don't do it recursively. Recursion will take exponential time to implement. So we're going to fill a table, right? So let me also show you a table. So how to fill the table? I have an example. So I is going from 1 to n. right? So the first column till P of I, right? So P of 1, if it is 10, let's say till P of I. So all this is going to be W1, right? If you want a profit of at least 1, so you can, this is all going to be W1. And after this stage, if you want to make a profit which is bigger than P of I, it's all going to be infinity. So infinity indicating that you can't make so much of profit. Okay, size of the knapsack that is required to fill this is n. So now once you know how to fill the first row, the second row can be filled, because in order to fill the ith row, what I need was only the values of w of I minus 1, right? So both of them, just the previous row is required. So you can just go to the previous row. From the previous row, you can compute the value of this. So one will be the just previous one will be the previous one, j minus 1. So there will be two entries. So you have to compare these two entries and pick the one which is minimum. So you can fill the second row, you can fill the nth row. Okay. So this P is the maximum profit that's possible. So NP will be the, if you pick all the items, you should be able to pick this much of profit, right? Now, if all the, not all of them will be P, right? So this is the maximum, since the P is maximum among all P, NP is the upper bound for the optimum, right? So you may not be able to make so much of profit, but something smaller than this. This is the upper bound. Okay, so yeah, just use this as a DP table. Yeah. So in order, so this is a DP table of size n cross np. So the size of the table is n square p, right? N into p, right? So I varies from 1 to n. This j will go from 1 to np. So the size of the table is n square into p. In order to fill one entry in the table, what you need is the min of two things. So this is each entry in the table can be filled in order one time. So the total complexity of filling this table is order n square. Okay, and the space as written now is order n square. But if you just want to find what is the maximum profit that you can make, you can just use two columns. But if you want to find what are the items that you need to pick in order to make so much of profit, that will be that would require a table of order n square. Yeah, correct. So you, even if it's a recursion, you can always rewrite it and make it as a top-down DP, right? So yeah, correct. So you have to store the results to optimize it. If you don't store it, if you just write it as a recursion, then it's going to take exponential time. Okay. So now how do, so I started with the knapsack problems. What is a knapsack problem? I've given you weights and the profits. I want you to find some items which will fits into the knapsack W. So the W has not yet come into picture, right? So there is a, in the size of the knapsack W which is given to us. We want to pick the item such that all the items fits into this knapsack. So I want to pick the item such that sum of the WI's is smaller than W, right? So I want to pick items such that the sum of the weights of the item is smaller than W, but I want maximum profit. But how do I figure that out from this table? This table doesn't give you this answer directly, right? But can we use this table to get the solution to the knapsack? Okay, so far in the equations, W has not come into picture. Okay, so that can be found out from the table. For example, if you go to the nth column essentially says that you're using all the n items. So if you go to the NP here, this will give me a number. This will give me a size of the table. If you give me, if you're allowed to use n items, and if you want to make a profit of NP, this is the size of the W that is required. Okay, so if it's NP, maybe, so you see that after a certain stage, everything is going to be infinity or large numbers. So if you want to make more profit, then the size of the knapsack that is required is going to be increasing, right? I repeat, if you want to make more profit, you need a bigger size knapsack. So if you look at any row, the sizes are all going to be increasing. So what I do is that I go to the last row and start traversing back. So as long as numbers while my w of I comma j, so I'm going to the nth column. So my I will be n, right? While n comma j I'm going to start with np. Okay. While w of I comma j is strictly greater than the capital W, then I will decrease my j. Okay. Since the size of the knapsack that is required is more here, I keep going to the left hand side. I stop the first time when I see a number here which is strictly smaller than or equal to W. When the size of the knapsack that is required is smaller than W, I'll stop. The corresponding J that I have, that is the maximum profit that I can make, right? So what is he saying? If you are allowed to use all the n items, and if you want to make a profit of J, then this is the size of the knapsack that is required. If the size of the knapsack that is required is smaller than this particular W, which is the size of the knapsack that's given to me, that's where I stop. Okay, and report this W, right? So while W of n comma j is greater than W, I'll just do j minus minus. When you come out of this loop, whatever is the j, that's the maximum profit that I get. Okay, with a order n square p table, I'll be able to find out what is the maximum profit that I can make using this dynamic programming table. Is this clear to everyone? Any questions? People have questions. I think you should ask the questions. Otherwise, you'll not know whether you have understood or not understood. Okay, so once we have we have a way to solve this problem using DP. But we started by saying that this is a 0-1 knapsack is an NP-hard problem. But we have already given a DP solution for it. So why is this not a good solution? So the complexity of this algorithm actually depends on P, the values that are involved. Okay, it doesn't depend on the number of numbers. So the P is the maximum profit. This could have a value of 10 to the power 10, right? 10 to the power 18. So my profit can be can be represented by any integer, which the integer can be of a 64-bit integer. Okay, in that case, my maximum profit could be 10 to the power 18. Okay, but if I want to implement this, I need a size of the table which is n square into 10 to the power 18. So we don't have so much of memory to implement. Okay, so in other words, the size of P is actually very big compared to the number of items. But the amount of space that is required, even if my integers weights are all integers, this just takes a 64-bit integer to represent a 10 to the power 18 number. Okay, so in order to represent a 64-bit number, what I need to give you is only 64 bits, which is a constant in terms of n. N could be 1000 or 2000. But each of these values, in order to represent the size of the input, is only 64 bits. But the size of the number itself is big. Okay, so when we say that something is polynomial, it should be polynomial in the size of the input. Okay, so the size of the input is, if you want to give an integer, our assumption is that each integer will only take constant amount of time, because we have 64-bit registers, then 64-bit is what is required to represent an integer. So so the 64 is a constant, right? So we will only measure the number of integers that you take, which is the size of the input. Okay, so but the complexity of the algorithm will depend on not on the size of the input, but it is a very huge number P, right? So which is 10 to the power 18. So in practice, this algorithm cannot be used because we don't have so much of space, and even time n square into 10 to the power 18 will take several years to give the answer. So this kind of algorithms are called pseudo polynomial. These are not really polynomial in the size of the input, but if you consider this P, this is called this makes the algorithm pseudo polynomial. Strictly, this is not a polynomial time algorithm. This algorithm, when the integers are above of 10 to the power 8, will not be useful in real life. Yeah, so this is not exponential. It depends on, it's not even exponential, right? So what I'm saying is that it's very large number. So if it has to be exponential, then it has to be 2 to the power n or something like that, right? So here the P, yeah, in terms of P, it is 2 to the power 64, right? Which is a very large number. That's what makes this That's what makes this algorithm not very practical. Okay, so that's the reason why this problem is NP hard. So that's the problem why this DP solution is not very useful. So this will be useful if P is very small. So if the size of the profit, maximum profit that you can make is about 1000, right? Then this is n square into 1000. You'll be able to implement easily if n is about 100. Okay, but if is m is 100 and p is a large number like a 64-bit integer, then this is not useful. So it's also known that there are no polynomial time algorithms to solve the 0-1 knapsack problem, because you can just write it as an integer linear program. And you know that ILPs are NP hard. We don't know how to solve ILPs. LPs are solvable, but ILPs are not solvable in polynomial. Okay. So I'm going to use this particular version of the dynamic programming to design algorithms which will give us, even when P is very large, this kind of algorithm can be used to get an answer which is very, very close to the optimum solution. Okay, it may not give you the exact optimum solution, but it will always guarantee you very close to the optimum. So how close you want, you can decide. You can take any epsilon. You want 1% closer to the optimum, this will give you 1% closer to the optimum. But if you want to get very close to the optimum, then the complexity of the algorithm will depend on how close you want to get to the optimum. Okay, we will see the more specific examples, more specific equations in this. So what I'm going to do is that these P of i's are very large. So what I want to do is that I want to do what is known as rounding. I want to make it smaller by dividing by some appropriate number. Okay, so this process is called as rounding. When the numbers are very large, I divide this by some constant, and so that all the numbers become smaller. When all the numbers are smaller, then you can apply DP and get the solution. But after you do the rounding, so whatever solution that you get, right? So what is the solution that you get here? The last line will only tell you what is the size of the knapsack that is required, and this is J is the maximum profit that you can pick. From this table, you can also figure out which are all the items that you need to pick in order to make a profit of J. Okay, so that is easy. That's a simple dynamic programming take. So you go to W of I comma J, it should have come from one of this. If W of I comma J is equal to W of I minus 1 comma J, that means that the ith item has not been used. Okay, so in that case, you just decrement your I. If this is not equal to this, that means that you have used the ith item. Just note down that you have used the ith item. In that case, I will anyway decrease by 1, but the J will also be updated to J minus P of I. From this table, you can also figure out what are all the items that you need to make in order to make the maximum profit. So the technique that I'm going to use in order to design approximation algorithm is do the rounding. Rounding is done on the profits, not on the weights. Okay, weights will remain the same. The size of the table that I'm building here is independent of the weights and the size of the knapsack. It only depends on the profits. So I'm going to round off these profits, and for the new version where the profits are all small, I apply this dynamic programming solution and get the solution. Right? When I get the solution, I will know what are all the items that I pick. Okay, once I get the solution to the rounded off option, I'm going to claim that that solution will be closer to the optimum solution to the original problem. Okay, when I say that I will find the solution to the rounded off solution, I will identify these are the items to be picked. The S is a subset of items, that is a solution space, which needs to be with the algorithm will pick, which is a set of items that our algorithm picks. Once you decide which are the items to be picked, you go back to the original version of the problem where the PIs are the original PIs. So the maximum profit that you can make, you will be very close to the optimum value. So the solving the rounded version is not same as solving the problem on the original problem, but you don't lose too much by rounding down in this case. Okay, now how do you do the rounding? Intuitively, if you want to get closer to the answer, the rounding will depend on that, right? So if you want to get very close to the optimum, then the rounding should not be too much. right? So if you make all the 1 lakh numbers as 10 numbers from 0 to 9, then you have done too much of rounding. In that case, when you go back to the original solution, you will lose too much. Okay, if I have 10 to the power 8 numbers, there are two options. One is to round it to 10 to the power 5. Another one is to just to round it to 2-digit numbers. If you round it to 2-digit numbers and solve the problem and go back to the original solution, you would have lost, there would be a lot of gap between the optimum solution and what you have found. But whereas if you have just reduced it to 10 to the power 5, right? So from 10 to the power 8, then that solution that you get will be closer to the optimum. That's the intuition. So so what we assume is that you're given an epsilon. Then I want to find an algorithm which will give me an answer which is at least 1 minus epsilon times the optimum. Okay, epsilon is any number which is greater than 0. I want to design an algorithm such that the solution given by the algorithm A is greater than 1 minus epsilon times the optimum. Okay, so this is the maximization problem. So this will be slightly smaller than 1. Okay, so let's get into the details how to get this. So epsilon is what is given to me. I define k, which is p into epsilon divided by n. So this would imply that k into n is epsilon into p. Epsilon into p, yeah. So p is the maximum profit that you can make. Epsilon is the epsilon that is given to me. This is the error factor, and n is the number of items. Let k be this number. Okay. So now all the profits you divide by k and take the floor value of it, because I want all the p of i's and the w of i's everything to be integers. When I do p of I divided by k, what I get is a fraction. So just keep track of the floor integer part of it. That will be your new p of i's. I'll call it as rounded down version of the problem. So the profits here are all denoted by p of I dashes. Okay, I divide by k, where k is a large number. So when I divide this p of I by k, what I get will be smaller. Now the p of I dashes will be smaller, relatively smaller. Okay, so two things that I want to remember here from the floor function is just straight away follows that. So the p dash that you get will always be smaller than p by k. Okay, p dash is floor of p by k. So p dash is always going to be smaller than or equal to p by k. So that means that if you multiply on both sides, you get this equation. This this just follows from the floor function. Okay, but p dash of, if you add 1 to this, right? So this you look at it as 2.5, right? So the 2.5 p dash is this will be 2. 2 is always going to be smaller than 2.5. But if you look at just one, subtract 1 from here and make it as 1.5, right? Then this number is going to be bigger. So the p dash is always certainly greater than p by k minus 1. If you do a minus 1, obviously this is going to be greater. This is going to be greater than this because this is the floor of it. Okay, and this equation is true. These two equations directly follow from the way I am doing the rounding. So now let's say O is the optimum solution to the original problem, right? So O is the set of items that you pick in order to get the optimum solution, optimum value to the original problem. Well, there are two problems. One is the rounded down version of the problem. The other one is the original problem. So what we want to solve is the original problem, not the rounded down. So we are doing the rounding so that it becomes easier for us to solve this problem in the rounded down. Once you solve the rounded down version, what we'll do is that we'll just take the solution. Just look at what are the items that I need to pick in the rounded down version. Same items I'm going to pick in the same items are picked. It's just like in the after you round down, let's say that my solution says that 2, 5th and 11th item needs to be picked. I just go and pick the same items in the original solution, right? That's what is the solution. But O here is the optimum to the original solution. So because of this equation that I'm writing here, if you add up if you multiply on both sides, what you get is the k times pi dashes is greater than pi minus k. Right, so if you add up all this equation, sum of all the items in the optimum, if you add up, what you get is that k times k comes out This is profit of all the items. This is basically the sum of all the items in O. When I write P dash of O, P of O, P dash of O is you're finding the sum of all the items in O, but you're adding your Pi dashes. Okay, here the P of O essentially means sum of all the items with the original weights. So this equation, so and the number of items in the O will always be smaller than n. Okay, so from here this equation straight away follows. If you just take up sum of all the items in the optimum solution, what you get is on the left hand side, and the right hand side it will be sum n n1, which is the number of elements in no, which is the number of elements in the optimum, but that is anyway going to be smaller than n. So the entire equation will become greater than P of O. So I'll use this equation in the next slide. So there are two definitions now. S is the optimum solution to the rounded down version of the problem. So what is the solution? It will tell you what are all the items that I need to pick in order to get the optimum solution to the rounded down version of the problem. So how do you solve the rounded down version of the problem? Because I did the round down, right? So I did the rounding. The profit of in the newer version are all smaller numbers. So I apply DP and find the solution to this. So the maximum profit that I'm going to make, going to get will be denoted by P of S. Okay, P of S, S is a subset of the items that I'm going to pick. Okay, how do you decide which items to be picked? You work on the rounded down version of the problem, use the dynamic program to figure out what are all items to be picked. Now you go back to the original item and pick those items, right? Add them up. That is what is P of S. Okay. O is the optimum version, optimum solution of the original problem. Okay, so that's the notation. And we are going to write here P of O, which is the sum of the profits of all the items in the big of O. This we will call it as opt, right? So this is the optimum. Okay, so now the focus is on focus is on P of S. I want to show that if you go back, the dynamic programming will tell you what are all the items to be picked. If you go back to the original version and add up all the profits, the total profits that you get will be greater than or equal to 1 minus epsilon times the optimum. Okay, so by doing the rounding and reducing the size of the items to be P dashes, you have not lost too much. This is the OPT, this is the optimum solution. Okay, so that means that it's going to be a good approximation algorithm. This epsilon is connected to the rounding, right? So if you want to do the rounding, you're going to divide by k. K is defined as p times epsilon into n. Okay, you're going to divide by a large number, right? If epsilon is a very small number, then the rounding that you need to do will not be too much. Okay, and if p is very large, then the rounding is going to be large. Right? The rounding that you do will be proportional to p, but inversely proportional to the number of items, and it will be directly proportional to your epsilon. Epsilon is generally smaller than 1, right? If you want a very small rounding, then you'll end up dividing by a large number, right? Okay, so now we want to show rest of the proof is on this. Okay, so let's just pay attention. So the P of S that I have will be greater than K times P of S. What is P of S? P of S by definition is the sum of the profits of the items in S. Okay, so now the each P of I will be greater than K times P dashes. Okay, so using this part of the equation, so what you get is that P of S will be greater than K times P dash of S. So in the P dash of S, you are actually looking at, you look at all the items and find the summation of P dashes of all the items in PS. Okay, but the claim is that this is going to be greater than this number. So why is this true? Because in the rounded version of the problem, S is the optimum. So P dash of S is certainly going to be greater than P dash of O. So P dash is essentially profit of all the rounded version of the problems. Here, when you do P dash of O, it is the sum of the profits that you have made. But if you look at the optimum solution and if you look at the rounded values of that, right, that's what is P dash of O. S will be bigger because S is the optimum to the rounded version. Okay, O is only the optimum to the original problem. But if you look at the rounded profits, you should have made more value by looking at the S. Okay, so now I'm just going to use the other equation that I wrote. So here, K times P dash of O will be greater than P of O into minus K, NK. That's what I'm going to plug in here. Okay, P of O is, as I said before, it's the optimum, right? And K times N, so the K and N is chosen in such a way that K times N is epsilon into P. K times N is chosen as epsilon into P. So what I'm going to get is, I'll replace K times N with epsilon P. Okay, so I wrote here epsilon P. But I am going to use the fact that optimum is always going to be smaller than P. So as I said, each of the items can fit into the knapsack. So the optimum value will always be greater than the maximum profit of any item, right? So optimum value will always be greater than the maximum profit that you can make. So the opt is always greater than P. Okay, so if you plug in these two values, you get that optimum is this. So you can take optimum as common. So what you get is the solution to PFS, which is greater than 1 minus R epsilon times the optimum. Okay, so the idea here is round down. When you round down, the values become smaller. Once you do that, then you find the pick up the items which will give you the maximum profit with respect to the new profits. Whatever items that you picked, that is items, you go back and pick the same items in the original problem, right? That's what is the solution. You may not get the optimum, but what this proof tells you is that this will be very close to the optimum. How do you do the rounding will depend on the epsilon, how close you want. Let's look at what is the complexity of this. So since P dash is going to be the maximum profit after rounding. Okay, so the complexity of the algorithm, if you write down the dynamic programming, will be n square into P dash. But how does P dash compare? So n into K is epsilon into P. So I wrote it as NP is equal to P by K. So the P dash is basically P by K, right? So the P dashes were defined as P by K. So the maximum profit, capital P dash is the maximum profit after rounding. So the maximum profit after rounding will be roughly equal to, it's not equal to, it's roughly equal to P by K, where P by K will be n by epsilon by the choice of my epsilon, K. K is chosen as n into P by epsilon. So if you rearrange the terms, you get that n by K is equal to n by epsilon. So I'll just replace this n by epsilon to be n by the P dash by n by epsilon. The complexity of the algorithm here is n cube by epsilon. This is independent of P. It only depends on epsilon. So this is n cube by epsilon. If you take epsilon to be, let's say, 0.01, right? So then what this theorem is saying is that you will get an answer which is close to 90% of the optimum. The complexity of the algorithm will be n cube by 10. But if you take epsilon to be 1 by 100, so what this is saying is that you are getting very close to the optimum. So if 100 is the answer, you will get certainly an answer which is greater than 99. But the complexity of the algorithm will be n cube by 100, right? So if you want to get very close to the answer, then the complexity of the algorithm will blow up. So how will it blow up? It is inversely proportional to the epsilon. Okay, so notice that the running time here is only not n to the power epsilon, it's actually a constant 1 by epsilon. So the running time is polynomial in n and 1 by epsilon, right? This can be read as n cube into 1 by epsilon. If epsilon is the error factor, you are trying to get very close to epsilon. The running time of the algorithm is polynomial in n cube and 1 by epsilon. So since the complexity is polynomial in n and 1 by epsilon, so this type of algorithms are called fully polynomial time approximation schemes. In short, it's called as FP dash. So for an NP hard problem, this is probably the best that you can expect to do, right? So because I am saying that if you want to go to 99% close to the answer, you can go. The running time will not blow too much. So 99% will be 100 into n cube, right? Which is a constant. The 1 by epsilon, if you treat it as a constant, you more or less have a polynomial time algorithm, right? So these algorithms are inversely proportional to the error factor, right? But you can't really make epsilon to be 0. If you make epsilon to be 0, then you'll get in the cube solution. But if you make epsilon to be 0, the running time of the algorithm becomes infinity. Okay, but if you make it very close to 0, it's still possible to get efficient algorithms. So the running time, so this is fully polynomial in terms of 1 by epsilon. There is no p here. I got rid of p. Okay. Summary is that for an Knapsack problem, there is an fp dash. What is fp dash saying? You can get answer to very close to 1 minus epsilon. The running time will be n cube by epsilon. And the technique that we used here is basically the DP, and the technique, another technique that I used is round down. So if there are questions, we can take it. Otherwise, another 10 minutes, I want to just talk about one more problem. Any questions so far? You can ask questions later as well. But if you have any questions right now, you can ask me. Okay, so let me continue with the next problem. If there are questions, we can take it up later. So the next problem is to find a max cut. Let me quickly define what's a cut. So you're given a weighted graph. Okay, a subset of a proper non-empty subset is called a cut. Okay, in general, S comma S complement, right? So S complement is essentially S dash, where S dash is a set of all numbers which are not there in S. You take a subset of vertices, you call it as S, and S dash is the set of all vertices which are not in S. Okay, and that's called as a cut. The only condition is that this has to be a non-empty set. It should not be non-empty, so that and it should be a proper subset. It should not be the entire V. Okay, if S is a proper subset and it's not empty, the same property is also going to be true with the S dash. You see, S is empty, then the S dash will be the whole set. If S is the whole set, then S dash will be empty. So if the number of numbers that I'm going to pick is between 1 and n minus 1, then S dash will certainly take numbers between n minus that. So that will also be between 1 minus n. So the both will be valid proper sets. Both will be non-empty sets. So you can take this as this is a set edge, and this is the set of vertices which are not in S. That is V minus S. Now this is called as a cut, and you take any edge where one of the endpoint is in S and the other endpoint should be in S complement. In other words, exactly one of the endpoints of an edge should be in S. Such an edge is called a cut edge. If both the endpoints are in S, it will be like this. If none of the endpoints are in S, then it will be like this. We don't care about the edges which goes with inside S. We don't care about the edges which goes within S dash. We only grow edges which are cut edges, which where exactly one endpoint is in S and the other endpoint is not in S. Such an edge is called cut edge, and the weight of a cut is the sum of the weights of the cut edges. You look at all the edges which are going across the cut, find the sum of the edges there. That is called as the weight of the cut. The max cut is a problem where you want to find a cut whose weight is maximum. Okay, the brute force way of doing it is you look at all possible cuts. So the number of cuts that are possible is 2 to the power n minus 2, right? The number of proper non-empty subset of n vertices is 2 to the power n minus 2. So that's clearly an exponential time algorithm. Brute force will not work. And this problem is known to be an NP-hard problem. There's a related problem called min-cut problem, right? So the min-cut is easy to solve. There are polynomial time algorithms. Those who have studied network for problems, max flow is equal to min-cut is a theorem. So if you know how to find max flow, you can also find the min-cut. But here the problem is max cut, right? Min-cut is among all the cuts, you give me a cut whose weight is minimum. So that is solvable in polynomial time, but the max cut is NP hard, right? You don't know how to solve max cut solution. Okay, so what I'm going to show you is a quick, simple two-off approximation algorithm to find the maximum cut. So the algorithm is called local search. What it does is that you start arbitrarily any set. You start with an arbitrary set as, okay, start with that set as your cut. Now you just find the weight of the cut. What are all the weight of the cut? You just look at all the edges which are outgoing from this cut and add them up. Okay. So now you try to move one node across the cut. You take a node in S and see whether this is right now it is here. If I move it here, what happens? The cut changes, right? So if you move an edge from here to here, the cut edge just changes. Okay. If you move a vertex from S to S dash, the cut edge just changes. If the cut changes and the value of the cut actually increases, then you move across. Similarly, you take a vertex here. See, right now it is an S dash. See whether you can move it to S. Only one vertex at a time. That's why it is called a local search. You try to move it across. If the total cut value actually increases, then you move. You try for all the vertices in both sides, in S and S dash. So every vertex, every node in V either belongs to S or S dash. You go through each of them. If it is an S, try to put it to S dash and see whether the cut edge, weight of the cut increases. If the weight of the cut increases, move it. Keep repeating this till for all the edges of all the vertices, if you move across the cut, either from left to right or right to left, essentially saying that either you move from S to S dash or S dash to or vice versa. Moving a vertex from one side to other side, if it doesn't increase the weight of the cut, you stop there. Okay, and the claim is that what we have will be a good approximation to the max cut. We cannot claim that there will be a max cut, but will be at least half of the max cut. Let's quickly look at the solution for this. Now let's look at a U which is in S. Now let's try to move it to S dash. So when you move it to S dash, the weight of the edge should not increase. If it was increasing, then my local search algorithm would have moved. Okay, let's just write down what does it mean. Okay, so if you look at all the edges which are where one of the endpoint is in S dash, right, that's the cut edge. U is in S, so you just, this is before moving. Okay, so before moving, you just look at all the edges where the V dash is in S dash. U is in S, right? So if let's look at this diagram, U is in S. Just look at all the edges which are outgoing from here. All of them will contribute to the cut edge. Okay, so that's the edge. Now if I move this to the other side, move this vertex to the other side, okay, so there will be some other edges which will become the cut edge, where the endpoint should be in S. So this is before moving the vertex. U is in S, so you just look at all the vertices which are in S dash. Look at the sum of that. Okay, and if you move V to S dash, if you move U to S dash, then you have to look at all the edges U comma V where V is in S. If V goes to the U goes to the right hand side, then the cut edges are all the you should look at all the edges where the other endpoint is in S. So this should not be, so the first one should be strictly greater than or equal to this. If this was smaller, that means that moving was useful to me, so I would have moved it. Okay, so this follows from the fact that algorithm stopped when moving doesn't help. Okay, so now what I do is that take this quantity and add the same quantity on both sides. What I get on the left hand side is 2 times this value. Okay, and right hand side, so this was already there. This is what I've added. Notice that this V belongs to S here and V belongs to S dash here. A vertex has to belong to either S or S dash, because your cut is a partition of the set of vertices. Okay, so what I have on the right hand side is sum of all the edges of the type U comma V, where one endpoint is U and the other endpoint can be any vertex in V. So this is true for any vertex which is in S dash when you try to move it to S dash. Same equation also will be going to be true for every vertex which is in S dash and write it this side. So whatever I wrote for S dash here, the same thing it can be written for every vertex which is in S dash. Okay, you can write a similar equation. I'll get another equation like this. If I add up that and this equation, what I get is the weight of the cut. Remember that U is here and V is in S dash. When I get the other equation, U will be in S dash and the summation will be over the summation over S. When I add up everything, what I basically have is 2 into the size of the cut. And this is going to be greater than weight of sum of all the edges in the graph. So notice that this has to be greater than the optimum, right? So optimum will only look at the cut edges and look at the weight of that. So what I have is sum of all the edges. Sum of all the edges, not all the edges will be cut edges, right? So the cut edges are subset of a set of edges. So the optimum value will be certainly smaller than or equal to weight of this cut, right? So so the left hand side when you add up, so what you get is so this should be written as greater than or equal to here. When I add up on the left hand side, what you get is 2 into the weight of the kite, which is greater than or equal to total sum of the weights on the kite, which is going to be greater than optimum. So this you can write it as CFS is greater than or equal to half of optimum. So what I have is a half approximation algorithm. Okay. So here you are just taking the very simple greedy algorithm is just try to start with any arbitrary value, try to move it to other side. If the weight of this optimum solution objective function actually increases, move it. Otherwise, don't move it. The simple this technique is called local search, and for this problem it works, and you get a half approximation algorithm. It's a very simple algorithm to find the max cut. So this is not the best known algorithm to solve the max cut problem. There is a so what I showed is 0.5. We should get very close to the optimum. So what is best known has a complexity of about 0.878. This is the technique used in getting this algorithm is what is known as randomized rounding and semi-definite programming. Using semi-definite programming and randomized rounding, you can get a algorithm which has the approximation factor to be 0.878. And that's the best that you can do if you assume the unique gain conjecture. In the vertex cover also, I talked about the unique gain conjecture. If that is true, then for the vertex cover, 2 is the best that you can do. Okay. If you assume a unique gain conjecture again, then the best that we can do is 0.878 for the max cut problem. But if you don't assume unique gain conjecture, then it has been proved that you can't do better than 16 by 17 unless p is equal to np. Right? So if p is equal to np, all np hard problems are solved in polynomial time. In that case, you get the solution. It's been proven that it is np hard to approximate within a approximation factor of 16 by 17. 16 by 17 is about 0.93. Okay, so this doesn't assume anything. So this result assumes a unique game conjecture. As I said, it's a conjecture which most people believe that it's true, but there is no proof that it's true, right? So if somebody proves it, then it becomes a unique game proof, right? So it no longer continues to be the conjecture. So provably 16 by 17 is the lower bound. You can't do better than that, but there's still a gap between what is achievable and what can be done. But the local search technique will only give you half approximation, which is not very close to what is best available. I think I'll stop here. So I think we stopped about 3 minutes late. Okay. So if there are questions, we can spend some time answering the question. Otherwise, we can post the questions in the link that is provided to you. I will answer the questions there today. Since there are only a few guys, if you want to unmute and ask questions, or if you want to write in the chat window, everything is okay. We have time for 1 or 2 questions. So I think the session was supposed to be till 4 o'clock. Okay, so I finished early. So I
Sir,
thought it
could
was till
you
3:30. Yeah.
briefly tell about unique game conjecture, sir?
Okay, so unique game conjecture, I don't think I'll be able to make a justice about saying what it is. Just say conjecture. I don't think I'll say more about it. You can read up in the this thing. So if you have to really understand what is unique game conjecture, it will take more efforts. There's no short answer to this question.
Thank you,
Okay.
Professor Muralidhara, for giving this interesting talk. And we
Okay.
can conclude the second day of summer school. Tomorrow we will continue at 10 a.m.